As an example of a shooting method solution to a boundary value differential equation, we're going to take a look at a very classical example in fluid mechanics. It's problem 1130 in your textbook and describes the Blasius solution to the Navier-Stokes equation for laminar boundary layers. Now this is hardly recognizable as Navier-Stokes because it has been massively manipulated into sets of non-dimensional coefficients. The definition of the principal remapping eta is given by y times the square root of u infinity over nu x. So y is height, u infinity is more or less fixed, and the specific value of which for us in this problem is of little consequence. Nu x is a term that is somewhat analogous to Reynolds number as a function of x. The other term of physical significance here in this problem that we're really actually probably chasing is the boundary layer velocity profile. The classical image there is depicted so that free stream is uniform. Yeah, when in existence over a plate in a stable laminar boundary layer, you get some unknown velocity shape. That unknown velocity shape is what we're trying to solve for. And the ratio of velocity over v infinity is actually the derivative of eta with respect to f. Or df with respect to eta, excuse me, flip that. So that's what we're actually looking for physical significance. The rest of the remapping is just a fallout of non-dimensionalizing this equation in pursuit of a closed form solution. Let's take a quick look at the boundary layer boundary conditions. I say that 4 times fast. Given to us first. Dimensionless function f at 0 equals 0. If I remember my Blasius solution theory background correct, the particular crossing of the dimensionless function is irrelevant. You're mainly interested in the velocity profile, which is given by the derivative of the dimensionless function f. So this, I believe, can be set to an arbitrary intercept. Second boundary condition, the slope of f with respect to eta at eta equals 0. So the slope being 0 means that the velocity is 0% of u infinity. If you look at that relationship, that makes sense. U over u infinity has to be 0, so velocity at wherever eta equals 0 corresponds to is nothing. Well, let's look at eta equals 0. When eta is 0, the only way to really achieve that is to make y 0. So this second boundary condition is no slip of the wall, remapped into this non-dimensional form called the Blasius solution. So that's just the no slip of the wall boundary condition. Makes sense. The next one in line, del f d eta, that is the velocity percentage here. So df d eta here is the ratio of u to u infinity. That equals 1, meaning that the local velocity has reached the value of velocity for u infinity, the free stream flow at an infinite eta. Okay, what variable can we change in eta to make eta infinite? The only variable to really adjust, that we have the freedom to adjust, is y. So eta equals infinity means you are so high up in the boundary layer, like way up here. So somewhere an infinite distance and height away from the flat plate that's creating the boundary layer in the first place, we know that the flow returns to free stream velocity, an infinite distance away. So those are the 3 boundary conditions given to us. We need to find the overall solution for f as a function of eta, and thankfully there is a code that can help us with this. So problem 1130, it's a script. If you look, a lot of these setups here are just handling the boundary conditions, setting all the different points, and then the heavy lifting. The first initialization is done here by ODE45. Then the iterative heavy lifting for the shooting method is performed there in line 11. All the logic about how to do the interpolation and sequential improvements of the boundary layer boundary conditions. Oof, I always get those confused. Is handled there in lines, I guess, 13 through 26. And let's look at the results it actually generates for us. Yeah, go ahead and change folder, do what you got to do. 2 unique solutions, of which this is probably the first to look at. Dimensionless function f, it does satisfy that it crosses 0 at 0. And the slope of f versus eta ends up determining the velocity ratios. So this, as far as I'm aware, has limited physical significance. Because like before, we want to look at the derivative of f with respect to eta that gives us the boundary layer profile. And this starts to look very familiar if you've seen many laminar boundary layer depictions. You see a very linear, a straight increase in velocity with respect to eta, which remember, eta is height above the wall. So this actually may be better if the 2 axes were flipped. But as eta increases from 0 to infinity, actually, the velocity grows towards unity in a linear fashion until finally it does over here in a stable manner start turning the corner and maxes out just at 1. So again, that's the boundary condition it was forced to hit, right? When eta equals infinity, which I think in this case they approximated is 6, because 6 is approximately infinity. If you look at the non-dimensionalization of the problem, it makes sense. But when eta reaches a very large number, you've seen that it intercepts the wall sufficiently at 1. The left-hand intercept is fine. All the other boundary conditions are met. If I can read them off right again. F at 0 equals 0. Yep. Middle boundary condition. Del F d eta at eta equals 0. So down here at 0, that equals nothing. Yep, so no slip of the wall is satisfied. And then del F del eta, so the slope, which is plotted directly here in the y-axis, at eta equals infinity, which is approximated by 6. Again, look at the physics. It makes sense. Equals 1. So yes,